Good afternoon, everyone. Thank you for staying with us. I will try to follow on the previous talk, and I would like to share with you our journey to a tool which we hope provides us a better data sets. We had an afternoon of talks using machine learning, which is so much dependent on the quality of the training data sets and also testing data sets. So that's something we have realized as well. And we realized we need to build a tool for us to have a better data set. And we decided to call it Ahoy. We wanted to have a very Czech name. And Czechs like to laugh at themselves, at their own expense. So Ahoy actually is the most common Czech greeting. That's what you would say if you enter the room. But it is originally a sailor's greeting. And we are not actually a real naval superpower in the Czech Republic, not having a single piece of sea. But that's one of the paradoxes. The second one is that it probably comes from the Latin phrase ad honorem Iesu, to the grace of the God. And we would be certainly the most atheistic country in the whole Europe, if not in the whole world. So I think that's a very apt name for the Czech tool. But how did we get there? So we have developed Radoslav from my friend's group, David Hoxha's group at Mathematical Physical Faculty, has developed a tool which is called P2Rank. It is a tool to describe ligand binding sites or predict ligand binding sites if you have a protein structure. And what it does is that it will throw a mesh of evenly distributed points on the surface of the structure. And for each point, it would try to predict whether it's ligand binding or not. Then it can cluster the points and rank them. And this way you would get a prediction. And in all sorts of comparisons, and Javier here would be probably more apt to talk about what is a good tool, but it seems to be quite a good tool. The problem here is that all these things are tested on the hollow structures of the proteins, like a Chen or Holo4K database, but not really on the APO structure. And you have heard a lot about APO and hollow structures, but still let me show you a short presentation, short video, which I think is really cool. This is a structure alignment of two structures of REF-ERP2 nuclear receptor, which is regulating circadian rhythms. The funny thing is that it's binding heme. So heme is not always only in the blood, but it can have other functions. You can see the ligand binding sites. You can define the ligand binding site residues. And the red one is the hollow structure binding ligand, and the blue one is APO structure. But you can also do a visualization where you will show the pocket with the space filling. And you see that the heme fits quite well in the red structure, but it will not fit at all in the blue structure. This binding site would be a cryptic binding site, and it actually appears in all the cryptic binding site data sets there are. So this is an example of the structure which would be really challenging for our tool. And Rado was always very unhappy with the performance of our tool. He said, it's just doing way too well. It can't be as good as it looks like on the data set. So let's build a data set of APO structures. And we thought this will be easy. We will probably download it from the internet, and in 5 minutes we will have it, and in the afternoon we will have results. But we couldn't find any data set of the APO structures. There used to be some, but they disappeared. As you have with the bioinformatics tools, the maintenance of those is difficult. So there were at least 2 or 3, but none of them was present when we were trying to get it. So we said, okay, we have to do it again. So we decided to build a tool, which we call Ahoy. And the tool was developed by my student, Christos Feidakis. And this tool can do not only simple apo-hollow structure pairs, but it does it, and that's crucial, for a specific ligand binding site. And it doesn't even have to be a ligand binding site, but it can be something very specific. I'm looking at Euroland. It shows the case because I was hoping you will come. This is I show you the example for the protein phosphorylation. So the ligand, in very loose way, could be post-translationally modified residue, like a phosphotyrosine in the Src kinase. It's also, I chose it because it's also my favorite protein. And if you do that, I will talk in a while how we do it, you will get a list of structures which have this specific binding site and do contain a ligand. And it doesn't have to necessarily be the phosphotyrosine, but in that place there is something else. And the list of structures which are without anything, this we would call apo. And the beauty here is that it doesn't show any structure which is Src kinase. It doesn't show the structures which have just SH3 domain, because SH3 domain doesn't have any bit of the binding site. You can define how big part of the binding site has to be there. That's in the options on the first page, but it's up to users. We use very loose parameters, but you can make it very strict. So you can say the full binding site has to be present, but also it could be just part of it. And there is some simple visualization tool here, but if you want to do more specific things, you can just click on the button download, and then you will get scripts for PyMol. And in PyMol, you can work a bit more with it. So that's the tool. In this, you can do any ligand. If you define structure, you will find the pairs. You can even do it for the water molecules. If you would be interested in specific water molecule, you can still ask whether there is something present in other structures. But it has to be for the same protein. And then we moved it a little bit further and built a database out of this. But you cannot build database for just anything. So we decided to do it for biologically relevant ligands only. And this you can search by free mode. But what are biologically relevant ligands? Here we take advantage of a fantastic resource, and that's a BioLab database from Zhang Group. So there are the ligands which have, in their definition, you need to have at least 2 contacts with the protein, a certain size, and there are like ligands which are on the blacklist, the ligands which would often appear in the crystallization conditions, solutions, and so on. And for this list of structures, we would build a database. How we do it? You define the protein. Using the SIFTs mapping, you will find all the structures for that particular protein. You look in them whether they have the binding site based on the strictness of the definition you have. And then you check whether the binding site is there. And if the binding site is there, you check whether ligand is there, and then you say it's apo or it's holo. So relatively simple thing. And with this, you would get a database which has about 500,000 entries at the moment, and you can search by 3 different modes. You can use search by the PDB ID, which would be very similar to the Ahoy, as I showed you before, but you can also search by specific UniProt. So you can say, find me all the apo-holo pairs for a specific protein, or you can search by ligand. So you could say, I have this ligand, find me all apo-holo pairs for this. And if you look at the example of the protein, this is P53, and you see here that we have like 175 structures containing P53, and each line describes a specific binding site, and there is a number of structures which are in apo and ones which are in holo form. So that would be the list, but then I will show you, you can dive deep into it, and I show you this on the example of the ligand search. In this case, I was looking for tenofovir, which is one of the most successful drugs they were for HIV treatment. And you will get, again, the list of apo and holo structures. And we have decided to add AlphaFold model, because why not nowadays? And I will talk about AlphaFold model in a while. And then you see some basic statistics about the similarity of the proteins, of the binding sites, TM scores, the surface accessible area of the pocket, and so on. These are to get some idea whether the binding sites are similar in the apo and hollow structure. So that's the basic functionality. And then you can do some statistics, of course, on the database, and I would just highlight maybe two things. One is that if we do that, we can actually get an idea how complete our information is. And then what we see is that we have, like, if we have a hollow structure, then only for about half of the proteins, we have also the apo structure. So we don't have the pair very often, actually, at the moment. And a lot of the binding sites are on the interfaces, either of the interchain, if you have a multi-chain protein, but also in between proteins. This would be then more difficult to classify in the AlphaFold cases I will talk about. And then you can look at some sort of statistics, and you would see, for example, that the apo structures are much more likely to have the binding sites with unobserved residues, that there will be some disorder. This would be explainable with the next slide, and something which Janet was talking about in the morning. So by far the most common binding site for us is a zinc binding site. And there are actually quite a lot of cases we don't see the apo structure. And the reason could be that it will often be zinc finger and it might be difficult to get it. So that we think that's one of the interesting things, that if the apo structure is missing, it could be that no one has tried to do it, but very often it will be because it's just very difficult to get the apo structure without the ligand bound. And there are other examples like chlorophyll and bacterial chlorophyll. There is not a single structure of the protein without the ligand available, although there are quite a lot of structures already. So I think in those cases, it's very unlikely that no one has tried to do that. It's just probably impossible. Okay, so what can you do with this, right? And for our sake, the reason was to try to build a better data sets, and I will show you how we do that. And with that, you could probably, if you succeed to build a better cryptic binding site prediction, and we have heard an interesting talk in the morning about this, it could help to expand druggable proteome. But we also want to use it to learn something about the binding sites and perhaps classify them in the case of the AlphaFold structures, and I will again talk about it in a while. So this is the thing with the cryptic binding sites. Here we don't really intend so much to build a better tool, although we will try to do that, but our main idea was to expand the data sets. And you've seen this today. There are two data sets for cryptic binding site. One is 93 pairs and one is 40 pairs. And they are not really like random. There would be still similar proteins in between them. And if we look at the Ahoy, what we did was, I can maybe go a little bit back to here. If the PRMSD, which is the RMSD of the binding site, was bigger than 2 between the apo and hollow, we said this is quite a big difference in the binding site. And if we chose all those cases, we could build a data set of 1,500, almost 1,600 apo-hollow pairs, which we think is substantial improvement on the previous ones. So this is an example of how we can expand the data set for testing cryptic binding site predictions. And I'm not going to talk about this in detail. There's a spoiler alert. If anyone of you is going to ECCB in autumn, then Vich Kerhag, who is the author of that, will talk about this in detail. And there was another project where, in the spirit of the Janet Thornton's lab, I thought it will be simple. So I tried to do that, but it turned out that it's actually much more difficult than I expected. the idea was that if you have the AlphaFold models, you actually don't know which state it is, whether it's Apo or hollow. And it could be interesting to know. And I thought it would be easy. I will just compare it. And here is just an example to give you about how much data we have. So if there are about 20,000 human proteins, we have experimentally solved structure for about 8,000 of them. And about 3,500 have the ligand bound, which was surprising to me. I thought there are much more with the ligand than without ligand, but in the case of the human proteins, it's not like that. There are almost 5,000 without a ligand bound. We were checking it, it looks like the algorithm is working great. And from these, we have the apo-holo pairs for about 2,000 proteins, and we are trying to process it. It's more difficult because the fact that you have very many structures gives a variety, and it's not always easy to decide and to choose the parameters, how to decide what is more similar to Apo, what is more similar to Holo. So we are working on this. So to conclude, we were trying to build a data set that is not based on the Holo structures to have more realistic and probably better test case. To do that, we built a tool that is available. You can try to use it, and also a database for biologically relevant ligand where you will find apo-holo structure pairs. And we found that a lot of structures are simply missing apo structures. A lot of proteins are missing apo structures. And it could be because of the disorder connected with the lack of the ligand in the binding site. And we have managed to expand the cryptic binding data set by the order of magnitude by using this tool. And I would like to thank my collaborators and the funding, Elixir and Gatcher, for their support. And thank you the most to you for your listening.
Let's thank our presenter. Do you have any questions? There's one here.
Hi, Marian. Great work from all you guys. So I've got two quick questions. First of them is, have you tried p2rank on these 2,000 proteins that you have up on holo pairs, and how does the performance drop? And second is, do you know for these 2,000 human proteins for which you have an upper holo pair, how many of those, like the proportion of those sites that actually changes? So the proportion of those sites that are cryptic or that go through a
so there are
change.
2 things. We have for the cryptic binding sites, we have 1,500, so not 2,000. And we did try that. I don't remember the results exactly, but it was a bit better than we expected. So p2rank can actually predict the binding sites on vast proportion of those places, even though there is a change. It's also, you get, it's PRMSD is an average value. So you can sometimes get a vast number by changing a lot one amino acid. And sometimes you have small changes. And whether it's the first one or the second one will discriminate whether p2rank can find it. And the other one, this 2,000 is the work has not been finished. So we still haven't managed to classify them either as holo or apo, but I hope we'll have that soon, and I will send you a message.
I have another one here.
Thank you for the talk. I have just a small question, a conceptual one. Is that like, when you're saying like I have 500 pairs of cryptic binding sites, what are the specific measures in the sense of what are the measures you do to consider a cryptic binding site cryptic? That's the thing.
Well, so at the moment we have tried. If I go back, so these are the data. These are the data we have from the Ahoy. So it's a volume, service, accessible surface area, TM score, and then RMSD and PRMSD. We have tried many of those, and in combinations, and it looks that we get the PRMSD as the best discriminator.
What is, sorry, the PRMSD, what is that? Sorry.
That's the RMSD of the residues which are forming the binding site.
Have you ever tried like doing docking of the ligand in the other structure? Like just saying.
P2Ran can do it now, but we haven't tried it systematically.
So we have time for one more quick one. You don't have priority, Rafi.
Good talk. Do you compare the APO structures to each other? Because obviously, like for a kinase, there could be multiple APO conformations.
So that's the problem we have with the classification of the APO versus holo. There is often so much variability between the APO but both also holo structures that it's not easy. We still try to figure out what to call an APO and what to call a holo structure, because we would like to associate it with protein, but you have so many structures, and sometimes there is a huge variability both in APO and in holo.
Do you check the alpha fold structures to see if they would bind the ligand? Like, are they the same as the ligand-bound structure? Because some of them, they could be APO or holo or something.
So that's what we try to do and we don't have the numbers yet. But in the end, we would like to have this, so to be able to classify ideally the structures. I think we can also do, when we don't have the apo-holo pair, we could still say whether it's similar to APO or whether it's similar to holo if just one of them exists. But there are definitely cases when it's the third one. It's not APO, it's not holo, it's still different structure. But I don't have the numbers, which I could tell at the moment. It's just something we are working on. It could just be wrong, of course.
Fantastic. Let's thank Marian once again.